Interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Ms. Stella or Ms. Patricia will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Good morning, everyone, and thank you for joining us today. I know that we're all excited to have our spring break week. I'm sure all of us need to recharge and give us some time to rest. So I do thank you for joining us today. I'll give a few seconds for those who are here to do Math 1324. Please, you'll find the link on the chat. Okay. All right. So for the rest of us, for today's session, we'll be doing the exam 2 review. Okay, so let's go ahead and get started. So exam 2 will cover sections 2.1 through 2.6. So let's start with backwards, right? Let's do a problem from section 2.6. Or information from 2.6. So 2.6 is all about rational functions. Rational functions are these functions that are fractions, right? So the first thing that we need to notice is that when we're dealing with rational functions or fractions, we never want our denominator to be equal to 0 because that would give us an undefined function, right? So we need to worry. There's going to be a restriction on our domain. So for A, if we're giving this function f of x is equal to 1 over x plus 3, and we need to state the domain, if we don't see it right away, what we can do is always set our denominator equal to 0, right? The x plus 3 equals to 0. And if we do that, we see that, here we go. I'm catching up to the slides. When we set x plus 3 equal to 0, we see that solving for x equals to -3. So if I were to put a -3 to that function, -3 plus 3 will give me a 0 on the denominator. Hence, it would give me an undefined or an error right on my calculator. So the domain for this problem would be all real numbers except that -3. So what we would answer would be this last one, right? D. All real numbers x except for x equals -3. Now, if we were to find or identify our intercepts, let's start with our x-intercept. To find our x-intercept, we all know by now, hopefully, that we just need to set y equal to 0. So let's go ahead and do that. So we set this function equal to 0. We have 0 is equal to 1 over x plus 3. And we're going to go ahead and solve for x by multiplying by x plus 3 on both sides. And when we do this, we see that we have a false statement. It says that 0 is equal to 1. So this false statement is indicating that there aren't any x-intercepts. So what we would put on our computer, our WebAssign, would be D&E, does not exist. There aren't any y-intercepts. Now let's to find the, x-intercepts. Now to find the y-intercept, we set x equal to 0. So let's go ahead and do that. Everywhere I see x, I'm going to plug in 0. So we have 1 over 0 plus 3. So 0 plus 3, and we simplify, is just 3. So we have when my input was 0, f of 0, our output, our y value, is 1 over 3. So in as an ordered pair or as a point, the answer would be 0 comma 1 over 3. Yes. All right. Now let's review our vertical and horizontal asymptotes. Okay. So now just a quick review. To find our vertical asymptotes are these imaginary lines that our graph cannot cross or touch. And these vertical lines are created when we have a restriction on our domain. So an awesome way or a quick way to find our vertical asymptotes is by first doing what we just did right now. Find the domain of these rational expressions, right? So um, several things that we need to also consider. Okay, we when we're finding the vertical asymptotes, we need to factor both the numerator and denominator, and hopefully we'll give an example of why this is important. Okay, but the main part is finding when the denominator is going to give us a zero. Okay, so normally um, all the places where x is equal to 0 for our denominator will become vertical asymptotes. Okay, and again, when we represent these in a graph, and for WebAssign, I know here they look like dots, but on WebAssign you would draw our vertical asymptotes as a dashed line. Okay, and again, these are lines that our graph cannot cross or touch. So if we look at our example that we have just been working at, we need to factor both the numerator and denominator. So as we can see, our numerator is already completely factored. We cannot simplify that anymore. We have a value of 1. And same with our denominator. Our denominator is just x plus 3. So there is nothing that we can factor from it. So now let's do it again. Let's set our denominator equal to 0, again, just in case we missed it. And we saw that x equals -3 is a restriction on our domain. Well, guess what? We just have the answer, the equation of our vertical asymptote. When x equals -3, this is the equation for a vertical asymptote. So when we draw this on our computer at -3, we're going to have this imaginary vertical line, okay, where our graph will not cross or touch. Now, let's look at the next aspect. Let's find our horizontal asymptotes, if any, right? So um, a horizontal asymptote are imaginary horizontal lines that our graph does not cross or touch. Now, there are several cases or scenarios that will give us a horizontal asymptote, and these are it right here. The first case or first scenario is we have to consider the degrees of our polynomials in our rational expression, right? So when we look at the degree of their numerator, if the degree of the numerator is smaller than the degree of our denominator, then there is a horizontal asymptote at y equals 0. Then at y equals 0, our horizontal line will have a horizontal asymptote. The second case, if the degree of our numerator is equal to the degree of our denominator, then we have a horizontal asymptote of this ratio. And the ratio is given by the leading coefficient of the numerator divided by the leading coefficient of the denominator. So again, this would be y equals this ratio, okay? And this happens when our degree of our numerator is equal to the degree of our denominator. And then finally, our last case is when the degree of the numerator is greater than the degree of the denominator, then there exists no horizontal asymptote. But as you see here in red, um, when this happens, we usually can have a slant asymptote. We won't have a horizontal asymptote, but we may have a slant asymptote. So let's look at our example that we've been working with. We have f of x is equal to 1 over x plus 3. And if we see here, again, let me write it again just to help out a little bit. My numerator, I can write this as this, x to the 0, because anything to the 0 power is going to give me 1, right? So here I can see that the degree of my numerator is 0, and if I look at my degree of my denominator, we don't write it. We always know that if there's no exponent, then there is a 1 there. So here it's easy to see that the degree of our numerator is smaller than my degree of my denominator. So hence, I am going to have a horizontal asymptote at y equals 0 because of our first case. So if I were to draw this on my rectangular coordinate system, at y equals 0, I have this imaginary horizontal line. And again, here's my vertical asymptote at -3. So now that we have these two things, we can um, further improve by graphing our equation. So we need to look at look and see what we have. So we have that it does not cross the x-axis. There are no x-intercepts. We do have a y-intercept at 1 over 3. We have a vertical asymptote at -3, and we have a horizontal asymptote at 0. So we want to do, to get a better sense of our graph, we want to plot some additional points, but we also want to be mindful as far as which points we want to pick. So for me, what I want to do is I would like to look at points that are to the left and right of my vertical asymptotes, and also since I have a horizontal asymptote, I want to also maybe pick some points above and below my horizontal asymptote. So in this particular case, um, let's look at these two additional points again at x equals -2, which is to the right of my vertical asymptote. Um, and let's pick 2, which is on the other side of my positive graph, right? So when x equals -2, my output or my y equals 1. And when x equals +2, my y equals 1/5. So I believe I put these points on here. Um, so let's pick some additional points. Um, let's pick at x equals -4. Again, now to the left of my vertical asymptote. And also let me pick x equals -5, a little bit further out to see what's happening with my graph. Yes? So when x equals -4, my y value is -1. When x equals -5, my y value is -1/2. So if I were to plot these points, I have these graphs, and hopefully when these points is enough to kind of generate our smooth graph. We know that our graph cannot cross the horizontal axis, so it's going to come from that line, but it's not never going to touch it or cross it, and it's going to come close, close, close to my vertical asymptote where, well, it will come really, really close, but never touch it or cross it. And then when I jump to the other side, okay, I know that my graph is coming from um, infinity up, right? So it's coming close to my vertical asymptote, had never crossed it or touched it. And then as soon as I get close to my horizontal asymptote, um, it's getting close to this horizontal asymptote, but it's never crossing this line or touching it. So when I try to do my smooth line, and again, I'm going to cheat, I'm going to use the computer to draw that smooth line and not my pen here or my cursor, you see that we have these irrational expression graph. So key points, we need to find all these points or information to do a graph. And again, on WebAssign is really easy to pick out the answers because they give us multiple choice, right? So again, if you have any questions, please let me know. I know we're doing a little review. If I'm going too fast, just let me know. Okay. All right. So let's look at this next example. It's just a little bit more complicated. So we have a rational expression where our numerator is 3x plus 2. Our denominator is x plus 3. So let's first state the domain of the function. And again, um, for us to find out what the domain is, we need to set the denominator equal to 0. Um, and when we do this, we see that x plus 3 is equal to 0. So we have the same situation as before. X equals -3. Okay. Now, also keep in mind, I know I'm jumping directly to the domain, but a lot of times uh, the domain is all the restrictions that we have on the denominator. When we need to factor both the numerator and denominator, that's going to alter our vertical asymptote, but it will never alter our domain. Okay, so and again, we'll give an example of this. So again, our domain is all real numbers except for -3. So our answer for this one would be this B one, right? All real numbers x except for when x equals -3. All right, so let's find our x-intercepts. Again, we'll set y equal to 0. We're going to multiply both sides by x plus 3. And when I do that, I'm going to get 0 is equal to 3x plus 2. I'm going to subtract 2 on both sides, and then I'm going to divide by 3 on both sides. So x equals -2/3. Okay, so I do have an x-intercept on this one, which is this. The equation of my x-intercept is x equals -2/3. Now let's find our y-intercept. Let's set x equal to 0. So everywhere I see x, I'm going to plug in 0. I'm going to simplify. And when I do that, I get a y-intercept. And that should be a y, not an x. I do apologize right here. This here should be y. So y equals 2/3. Okay. All right. So let's factor again. The factoring comes to determine our vertical asymptotes. So if both our numerator and denominator are factorable, it can affect our vertical asymptotes. So if we see on this case, 3x and 2, they have nothing in common, so I cannot factor any of that except for the one value, right? And same with my denominator. X plus 3 is already simplified. There's nothing that x shares with 3 or vice versa, so the only factor that's shared by both is 1. So again, they are completely factored. So to discover or find my vertical asymptote, again, I set my denominator equal to 0, which I have already done. And I saw that my equation of my vertical asymptote is x equals -3. This is my vertical asymptote. Okay. All right, so again, we represent this vertical asymptote as a vertical line, and it's this imaginary line that is represented in the graph as dashes, okay? All right, so let's find our horizontal asymptote. This one's more straightforward. I see that my numerator has a degree of 1. We don't write it. And my denominator has also a degree of 1. So now we're dealing with the case 2 for my horizontal asymptote, which says that when my degree of my numerator is equal to my degree of my denominator, I'm going to have a ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. So in this case, my leading coefficient of my numerator is 3. The leading coefficient of my denominator is 1. So my horizontal asymptote is y equals 3 over 1, which just simplifies to 3. So I have a horizontal asymptote, imaginary vertical horizontal line at y equals 3. Okay. All right. So we have these points. Let's pick some additional points to do our graph. And again, I like to pick points to the left and right of my vertical asymptote, and then a few points just to see where my graph is lying, right? So let's start here with x equals -2 and x equals +2 again, because this is what my vertical asymptote was -3. So this is to the right of my vertical asymptote. So when x equals -2, my y value is -4. When x equals +2, my y value is equal to 8/5. Okay, so now let me pick x equals -4 and x equals -5, which is the same points that I had picked before. And when I do this for x equals -4, I have a y value of 10. And when x equals -5, I have a y value of 13/2, right? So 13 over 2. So when I plot these points, again, I'm going to do a little cheating. I'm going to let the computer draw these points. Again, these are smooth curves that come very, very close to my asymptotes. They never cross or touch them. This is the graph to the left of my vertical asymptote, and these are the points connecting the points. These are the points to the right of my asymptote. Okay, so again, this is a review of our rational expressions. Okay. All right, Ms. Chuka, would you like to take this one on?
Yes, thank you, Mr. Carizales.
Of course.
Okay, so let's continue with another example for graphing these type of functions. So we're going to be covering these step A and step B and step C. So we'll start with step A, which is to look at is there any numbers that will restrict our domain. So as you can see in the denominator, we have the x. So if we set the x equal to 0, then we can see that 0 is going to be excluded from that domain. Okay, so my answer here would be all real numbers except for 0. Next, we can find the intercept by letting y equal to 0 and solving for x. So if I replace f of x with 0, then we can multiply by x on both sides. So x times 0 is going to be 0, and x times this expression here will give us x squared minus 9. Okay, so we get 0 is equal to x squared minus 9. Add 9 on both sides and take the square root. So we get x is equal to plus or minus square root of 9, and the square root of 9 is 3. So these are going to be our x-intercepts. And then the last step is to find the y-intercept. So we let x equal to 0. So we replace x with 0, then we get that our y-intercept is 0 squared minus 9 divided by 0. But here we cannot divide by 0. So we're going to have our y-intercept does not exist. So we enter D and E. And then next we go on to finding the asymptotes. So you want to make sure that you factor the numerator and denominator, because if in the denominator you had, for example, x minus 3, then these factors would cancel. And when you cancel these factors, it creates a hole in the graph. Okay. In this situation, we cannot cancel any of the factors. Okay, so we set our denominator equal to 0. And so our vertical asymptote is at x equals 0. And then we look at the degree of the numerator and the degree of the denominator. So we can see that the degree of the numerator is greater than the degree of the denominator. So that means that there is no horizontal asymptote, but we can check to see if it has a slant asymptote. So it's going to have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. And in this case, we can see that that is the case. And so that means that we're going to have a slant asymptote. So how do we find the slant asymptote? We can divide. So here, if I'm dividing by x, my c is 0. My coefficient for x squared is 1. I don't have an x. And then I have a negative 9. So if I do this division, then we can see these are results. So your slant asymptote is going to come from the quotient. So here I have a 1, so that's going to be x. So my equation for that is y equals x, which is going to be your slant asymptote. Okay, so so these are the information that we have gathered so far, and then we can plot additional points. But you want to do that after you plot the information we have, so that we can see where to pick these extra points. So here's my slant asymptote, my x-intercepts, and I didn't have a y-intercept, so I can choose some extra points. Some of us might be able to kind of see where the graph is going to go. We know it has to get close to the asymptote, but I'm going to go ahead and plot 2. So if I substitute 2 for x, we get 2 squared minus 9, which is 4 minus 9 gives us negative 5. And then we have 2, so negative 5 halves. If I use 4, then we get 7 fourths. Negative 2 is negative 5 halves, and then we get 7 fourths. So if we plot those points, then this is what they look like. And then we can draw our lines or connect the dots. And so our graph is going to come close to the asymptote, and then it shoots up. Remember that and then we have the other line coming down this way. Okay. So our vertical asymptote was x equals 0. That's why the graph is getting closer and closer to the axis here, but it's not crossing. Okay. And as you can see, the same thing, it gets closer and closer, but it's never going to reach it. So these were all examples of chapter 2.6. So now we'll start looking at other things. So this example is from 2.1, where it says write the quadratic function in standard form, identify the vertex and the axis of symmetry. So to write in standard form, I can separate it. I can separate the x terms here and parentheses. And then we're going to take half of 8, which is 4. I'm sorry, first we're going to factor out the 2, because remember that your x squared term has to have a 1 here. So if I factor out a 2, then I get 2 parentheses x squared plus 4x, and then parentheses plus 7. Now I can take half of 4. So half of 4 is 2. And then if we square it, we get So we're going to add and subtract a 4 into the parentheses, and then we go from there. So now we want to get rid of this -4, so I can take it out of the parentheses if I multiply it times the number in front of the parentheses. So 2 times -4 gives me -8, and then I simplify some more. -8 plus 7 is -1, and I can factor x squared plus 4x plus 4 factors as x plus 2 times x plus 2. Since they're the same factor, I can rewrite as x plus 2 squared. So since this is in standard form, I can get my vertex from here. So remember, your vertex is going to come from this number here and the outside number. So I have a plus 2, so my x coordinate of my vertex is going to be -2. And then my k, which is the constant over here, is going to be -1. The axis of symmetry is always your x coordinate of the vertex. So in this case, our x coordinate is -2. So our axis of symmetry is x equals -2. Okay, so this is taking a problem here in general form, writing it in standard form, getting our vertex, and then the axis of symmetry. And if you have to graph this, then you have your vertex. Then you would just need to find your x-intercepts and the y-intercept. Okay, so now we get into a little bit of 2.2, 2.3, 2.4, 2.5. It's gonna kind of bring in all those examples into one problem, for example. So it says find all the real zeros and determine the multiplicity of each zero. So this should be f of t is equal to t to the 4th minus t cubed minus 30t squared. And so there's different ways that you can solve this. Okay, so one way here is we can set the function equal to 0. So anytime that they're asking to find the zeros, that should be our first step, is set the equation equal to 0. Then ask yourself, can I factor anything out from my polynomial here? So notice they all have at least a t squared in common, so I can factor out a t squared. So t squared times t squared is t to the 4th. T squared times -t is t cubed, and t squared times -30 is -30t squared. And then in the parentheses, now I can see that I have something that's quadratic in here. So I can try to factor this as well. So I get t minus 6 times t plus 5. So now I can set each factor equal to 0. So 0 is equal to t squared, 0 is equal to t minus 6, and 0 is equal to t plus 5. And so if I solve for t, on the first one we get t is equal to 0. On the second one, if I add 6 on both sides, I get t is equal to 6. And if I subtract 5, I get t equals -5. So when it's asking for the multiplicity, basically it's asking you how many times does a certain zero appear. And if it appears an even number of times, then the graph is going to touch and turn. If it appears an odd number of times, then the graph is going to cross. So here, even though I only have one t equals 0, in reality, since the t is squared, there is another t equals 0. So 0 appears twice. That means that it has an even multiplicity. So it's going to touch and turn. At t equals 6, this appears only once. So that means that at t equals 6, our graph is going to cross. And at t equals -5, -5 appears once, so our graph is going to cross. And so I put the graph here so we can see that at t equals 0, it touches and turns. At 6 and -5, the graph is crossing. Okay. And then in a little bit, we'll apply the end behavior as well. Okay, so just a quick review on end behavior. I always like to look at these 4 graphs, because if I know these 4 graphs, then I can find the end behavior of any graph. So if it has an even degree with a positive leading coefficient, your behavior is going to rise to the right and rise to the left. If it has an even degree with a negative coefficient, then the graph is going to fall to the left and fall to the right. If you have an odd coefficient, an odd degree, and it's a positive leading coefficient, then the graph is going to rise to the right and fall to the left. And then if it's a negative leading coefficient with an odd degree, then it's going to go to the left, rise to the left, and fall to the right. So here in this example, we have 12x cubed plus 6x. Since it has an odd degree, that means that we're looking at either this example or this example, and it's a positive coefficient. So the behavior is going to act like this graph here that have my mouse going over. And so my answer for this, I would just write that the graph rises to the right and falls to the left. For the multiplicity, again, I like to use two graphs that we're familiar with. If I was to find the zeros for x squared, then my zeros are at 0, but there's two zeros, right? X equals 0, x equals 0. So it's going to touch and turn. And if I solve for x here, x cubed equal to 0, I would get x equals 0, but it appears 3 times, so it's going to cross because it's an odd number of times that it appears. Even though this kind of looks like it touches and turns, it's going to cross through x equals 0. Okay, so something else that we want to look at is the possible rational zero theorem, because it's going to help us find the zeros. So you want to look at the factors of the constant term, which is the last number, the term that doesn't have any x in it. And then the factors of the leading coefficient is the first, the number in front of the term with the highest exponent. Okay, so we take that information, and if we're applying it to this one, then our factors of 9 are 1, 3, and 9. The factors of 1 is 1. And we want to include both the positive and negative for each of those factors. So I can write them as plus or minus 1, plus or minus 3, plus or minus 9, divided by plus or minus 1. So if we divide, we get 1 divided by 1, 3 divided by 1, and 9 divided by 1. So on WebAssign, they don't have the plus or minus symbol, so you would have to enter it separated by commas. So negative 9 minus 3, negative 1, 1, 3, and 9. Okay, so if you want to find the zeros for this polynomial function, you could take your polynomial here, and if you are comfortable with trying to factor by grouping, then you can do that. Or if you are not sure how to factor by grouping, then we can use synthetic division. But the first step, let me go back here. The first step would be to find these possible rational zeros. And so what it does is it takes an infinite amount of numbers and it reduces it to only 6 numbers that we can check. I always recommend that you start with 1, and if 1 doesn't work, then you can try negative 1. And if that doesn't work, then we could try 3 and so on. Okay, so now we can go to step 2, and we can apply synthetic division. So we have a 1, a negative 9, and a negative 9. So bring down the 1. 1 times 1 is 1, plus 1 is 2, times 1 is 2, plus negative 9 is negative 7, times 1 is negative 7, plus negative 9 is negative 16. So we don't get a remainder of 0. That means that x equals 1 is not a 0. So we try the next number, which is negative 1. So if we keep going, negative 1 times 1 is negative 1, plus 1 is 0, times negative 1 is 0, plus negative 9 is negative 9, times negative 1 is positive 9, and then plus negative 9 is 0. So since we get a 0, that is going to make us happy, because that tells me that x equals negative 1 is a 0. But more importantly, if we take our quotient, it's going to be quadratic, because we started with x cubed and we broke it down, so it's going to be quadratic. So my quotient is x squared minus 9. And since this is quadratic, now we have options, right? We can use quadratic formula. We can try to factor. In this situation, we could use a square root property. And so at least we have options for solving this type of equation. And so I'm going to go ahead and use the square root property and add 9 on both sides. Then I can take the square root, and it gives me x is equal to plus or minus 3. So these are my 2 of my zeros, and our degree is 3. So since my degree is 3, I need to have 3 zeros. So my zeros are -3 and 3, which is what I got from here, and then -1, which is what we had from the synthetic division. And then the factors, in some examples, you might need to use factors. So to get a factor, we just add 1 on both sides. So we get x plus 1. Take the -3 to this side by adding 3. So we get x plus 3 and x minus 3. We'll use the factors in a little bit. Okay, so let's do one more example where it asks us to do everything and even to graph it. So if you have this example here, again, if you're comfortable with factoring, then notice here that they all have an x squared in common. So you could factor out the x squared from the beginning, and then that way you would be able to use, whatever's remaining in the parentheses is going to be quadratic. So it might be faster to factor than to list the possible zeros and so on. But since the question is asking to list the possible zeros, then we'll go ahead and do that. Okay, so my possible zeros, let me get my pen out really quick. My constant term is 0 because I don't have a number here, right? So my constant term is 0. So my factors for 0 is 0. And if I divide by, if I divide by my leading coefficient, my factors are plus or minus 1. So my only possible zeros is 0. So that is why I'm using 0 as my possible zero here. So if we take apply synthetic division, then we can use the coefficient. And give me a really quick second. Let me make sure turn my phone down because somebody's really wanting to get a hold of me here. All right. So now if we continue, we bring the 1 down. Or let me explain this here. So we have our 1 for the x to the 4th. We have a -1 for x cubed, -6 for x squared. And then I don't have an x term, so that's 0. And I don't have a constant, so that's 0. So we bring down the 1. We get 0 times 1 is 0. Plus -1 is -1 times 0 is 0. Plus -6 is -6 times 0 is 0. And we get a whole bunch of zeros. Now the good thing is that we got a 0 in the remainder. So that means that x equals 0 is a 0. But if we get our quotient, since we had an x to the 4th polynomial, when we write our quotient, we have to go 1 degree less. So that's going to be x cubed minus x squared minus 6x. So then we repeat the same process. Or again, you can factor out an x and you can get there quicker. But I'm going to go ahead and repeat the process. My possible zeros are 0 again because I don't have a constant term. So now I have 1 for x cubed, -1 for x squared, and -6 for x, and then I have a 0. So bring down the 1 times 0 is 0, plus -1 is -1 times 0 is 0, plus -6 is -6 plus 0, and we get 0. Okay, so if I break down my quotient, since I had x cubed, I'm going to begin with x squared minus x minus 6. So finally, this is quadratic. And so I can go ahead and try to factor. It does factor, but I went ahead and used the quadratic formula. So we plug in our b is -1, our a is 1, and our c is -6. If we do the work, then we get that x is equal to 3 and x is equal to -2. So again, x squared minus x minus 6, you could have just factored, but I went ahead and used the quadratic formula so that we can see an example with that. So we have x equals 3 and x equals -2 as our as 2 of our zeros. Okay, and my other zeros are going to be x equals 0 and x equals 0. And so x equals 0 appears twice. So we know that the graph is going to touch and turn. At x equals -2, the graph is going to cross. And at x equals 3, the graph is going to cross. Okay, so I did this example using the possible zeros, but just to emphasize what I wanted to share with you at the beginning is that from the beginning, you could have, let me get my pen out again. You could have just set this equal to 0 and factored out, oops, I don't know why this is doing that. Okay, x cubed and -6x squared. I'm using a new computer or a different computer, so I'm still learning how to use this one. Okay, so from the beginning, I can see that they have an x squared in common, so I could have factored out the x squared, so we would get x squared, and then we would have a minus x and a -6. And so now this part is going to be what we ended up with here. So at this part, you could just factor. So we would get x times x, and then we have 3 and 2. So that would be negative, positive. And then we have x squared is equal to 0. So now you can set each of these factors equal to 0 to get these zeros here. So there are different ways for you to approach the problem. And so I always like to tell my students, pick the way that you feel the most comfortable with, and then go with that method. Now, if you try to use this method all the time, just remember though that it doesn't work. Like not all polynomials will always factor. Okay, so in some situations you're forced to use the possible zeros and then find them using synthetic division. Okay, so now that we have our information, step C is to graph the problem. So let's go ahead and do that. So the first thing that I recommend is for you to plot your zeros. So on the next page, okay, well, I guess the turning points, to find your turning points, you take the degree, which is 4, and we subtract 1. So we have 3, maximum number of 3 turning points. And so if we plot our zeros, we get 0, negative, or positive 3 and -2. And then you want to apply the end behavior, okay, to the zeros. So my end behavior, since this is even and the coefficient is positive, what's going to happen to my graph? Anybody remember? If you have even and positive, is it going to be like a parabola going up, a parabola going down, or the cubic function, or the other cubic function? So the behavior, since this is even and this is positive, the behavior is going to rise to the left and it's going to rise to the right. Okay, and then we said that at x equals 3, the graph is going to cross. So I just put my graph, I just let it cross my x-axis here, and then over here it's going to cross as well because it only appears an odd number of times. Okay, so now we pick additional points. So I could pick a point all the way over here to the right or all the way to the left, but maybe what I'm more interested in is what happens in between my end behaviors here. So I'm going to use -1, I'm going to use +2 and +3. Okay, so if I plug in -1 for x to the 4th for all my x's here, then I get -4. So -1 gives me a -4, so that's right here. If I plug in a 1, then I get a -6, so that's going to be down here. And then if I plug in a 2, I get -16, so that's going to be down here. And then I can sketch my graph based on this information I have. But notice right here at 0, we said that the graph was going to touch and turn. Okay, so don't forget that your graph touches and turns at x equals 0. Okay, so I can sketch my graph. It touches and turns, it comes down, and then it goes up. So this is my graph that I drew on paper. And then the real graph, so you can see how it compares, is this one here. Okay, so I encourage you to draw it on graph on your paper first. And if you're using WebAssign and you have multiple choice, then you can go see which graph kind of matches your graph. Okay, or if you're taking a test in your classroom, like for my students, I ask them to take the test, and if it's a face-to-face class, you're gonna have to draw it out on paper. And so what I'm looking for is that you understand that it's crossing at the X-intercepts, or if it's touching, that you applied the end behavior and the Y-intercept, and then plotted a few extra points. Okay, so I'm looking at that information. Now, the next example is writing the polynomial given this information. So we know it's a degree 4. We have 3 zeros here, and then we have a solution point. Since it's degree 4, I'm missing a 0. So remember that if you have a complex 0, the conjugate is also a 0. So my zeros are x equals -4, x equals 1, x equals I, and x equals -I. So if I add 4 on both sides, my factors are x plus 4, x minus 1, x minus I, and x plus I. So I can set it up as a polynomial here. I use an in the front because I don't know what my leading coefficient is. And then I have my my factors. So I always like to multiply my complex numbers first. So I'm going to have x times x is x squared, x times I is ix, negative I times x is negative ix, negative I times I is negative I squared. We can simplify a little bit. So my ix and negative ix is 0. And so that leaves me with x squared minus I squared. And I squared is -1. So I end up with x squared minus -1. Simplify it out, and we get x squared plus 1. So then, and we get x squared plus 1. So then I multiply the next two factors. X times x squared is x cubed, x times 1 is x, -1 times x squared is negative x squared, -1 times 1 is -1. Gather my like terms if I have any. So then we multiply times the next one. So x times x cubed is x to the 4th, x times x is x squared, x times negative x cubed is negative x cubed, x times -1 is negative x, 4 times x cubed is 4x cubed, 4 times x is 4x, 4 times negative x squared is negative 4x squared, and 4 times -1 is -4. Gather your like terms. So I have x to the 4th, I have an x squared here, and a negative 4x squared gives me, so that should be, let me just double check it here, a negative 4x squared. Okay, so we're okay. So I gathered my x cubes, negative x cubed plus 4x cubed is 3x cubed. And then I have my x's, which is negative x, and a 4x is 3x, and then my -4. So now I can use my solution point. My solution point tells me that when x is equal to 0, I should get a -8. So what I can do with that information is I can let f of x equal to -8. And anywhere I see an x, I'm going to plug in a 0. And so if I simplify, I get -8 is equal to an times -4 divided by -4. So an is equal to 2. So my leading coefficient there is going to be 2. And if I multiply it out, 2 times everything inside gives me 2x to the 4th plus 6x cubed minus 6x squared plus 6x minus 8. And so this is my polynomial. So if you were to apply synthetic division and do all that work, you would end up with these 4 zeros. Okay. And I believe I have one more example that you're going to see. Some of us have it in our homeworks, or it could be on your test. It depends on your instructor. But here we have this function, and they tell me that 4 plus 2i is a 0. So the question is find all the zeros. So since I know that this is a 0, then I can just apply synthetic division here. So let's have 1, negative 12, 52, negative 80 comes from this here. So if I bring down my 1 and I multiply it times 4 plus 2i, then I get, yeah, these are fun, right? So I'm glad to see that somebody else likes them as well. So here we have 4 plus negative 12 is a negative 8, and then we have your imaginary part, 2i. So now we have to multiply this term times this term. Okay, so we're going to get 4 times negative 8 is negative 32, and then 4 times 2i is 8i. 2i times negative 8 is negative 16i, and 2i times 2i, 4i squared. Let's simplify and clean it up a little bit. Let me go back. Remember that I squared is negative 1, so that's where we're going to get a negative 4, and 8i minus 16i is 8i. Okay, so that's how we ended up here. So I added to the 52, so 52 plus negative 32 minus 4 gives me 16. So let me go back. So 52 minus 32 is 20, minus 4 gives me 16, minus 8i. So then we do again 4 plus 2i times 16 minus 8i. So 4 times 16, 64. 4 times negative 8i, negative 32i. 2i times 16 is positive 32i. And 2i times negative 8i, negative 16i squared. So your 32i's will cancel, become 0. And I squared is negative 1 times negative 16 is positive 16. Okay, so, okay, negative 1. And then we get 64 plus 16, which is going to be 80. Minus 80 is 0. So if you got anything other than a 0 here, then you know that you did something wrong in your addition or multiplication, because they told me at the beginning that 4 plus 2i is a 0. So that's going to be, this has to be a 0. So if we get our quotient, here we started with x cubed, so my quotient would be x squared for the 1. And then I have negative 8 plus 2i times x, plus my constant, 16 minus 8i. So since this 0 is 4 plus 2i is a 0, then the conjugate is also going to be a 0. So I can use my conjugate. So 4 plus 2i, the conjugate is 4 minus 2i. I can use that as well. So I have x squared is 1. Negative 8 plus 2i is my next coefficient. And then 16 minus 8i. So if we start the process, I bring it down, the 1 times 4 minus 2i. I'm going to add the real parts. Negative 8 plus 4 is negative 4. 2i times negative 2i is 0. And then multiply 4 times negative 4. Negative 2i times negative 4. And we get negative 16 plus 8i, so that gives me 0. And it should give me 0 because I know that's a 0. And then my quotient, since this was quadratic, now we break it down. So this is going to be x minus 4. Set that equal to 0. And we get x equals 4. So your zeros are x equals 0. Actually, that should say x equals 4. Sorry. So this is x equals 4. And then your 4 plus 2i that they gave me here. And then your conjugate of 4 minus 2i. Okay, so this x equals 0 should be x equals 4. These are some of these examples. Some of you are going to have your exam 2, maybe it was due this week, or maybe it's due on Sunday. Others might have it due Monday or Wednesday or Tuesday from the following week after spring break. So whenever you do have your exam, I wish you the best, and I wish you a happy spring break. And so I'm going to pass it over to the staff so they can tell us what's coming up after spring break.
Thank you, Ms. Chuka. Thank you, Ms. Chuka and Mr. Carizales, for your wonderful presentation. If you would like to download a copy of the presentation, you can go to the top right corner and click on the box with the arrow going down while the presentations are on the screen. That'll allow you to download the PowerPoints, and we also want to remind you all about the previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked was a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and remember to send your student ID numbers to us before you log out. Before you all leave, I want to share the TVE sessions that we will have next. Okay, there we go. At 1 p.m. today, we will have a presentation with the EPCC Mental Health Committee, and join us again the week after spring break at 11 a.m. for Happy Math Hour, where Math 1314 will be covering properties of logarithms, exponential and logarithmic equations, and Math 1324 will be covering basic matrix operations and inverses. Our 3 p.m. session will be EPCC Music with Yasmin Flores. Thank you all for coming in today. We hope you all have a lovely weekend and a restful spring break. If you have any questions, feel free to use the chat box or your mic, and we hope to see everyone for a happy math hour after spring break. Thank you, everybody.